Hello, welcome back to our course on Discrete Calculus with the Wolfram Language. My name is Alistair Forsyth, and this lesson will be on permutations and combinations. So permutations and combinations are the various ways items from a set can be chosen to form subsets. The word permutation can typically refer to three different things: a subset of a set in a particular order, the process of reordering an ordered sequence, or the number of possible permutations of a particular set. On the other hand, a combination is just a subset in which the order does not matter. So, when creating a subset of k elements from an existing set of n elements, we get the following two formulas. The number of possible combinations from the set, often denoted C of n comma k, is equal to n factorial over n minus k factorial times k factorial. The number of possible permutations from the set will be P of n comma k, which is equal to n factorial over n minus k factorial. A helpful identity of combinatorics is the Pigeonhole principle, which state that if k objects are chosen from a set of n objects where k is greater than n, at least one object is chosen twice. The reason it's called the Pigeonhole principle is that if you have a big birdhouse with a bunch of different little rooms for pigeons, and there are more pigeons than those pigeonholes, then there's going to be at least one pigeonhole with two pigeons in it. Similarly, if there are 367 people in a room, at least two people must have the same birthday, as there are only 366 distinct birthdays one can have. On the subject of birthdays, if we have 40 people in a room, what's the likelihood that two of them share a birthday? You see, this is a problem that we can solve using combinations. First, we calculate the number of possible pairs, which we do here in the Wolfram language by setting a combinations function and then taking combinations of 40, 2. What this represents is every possible way we could pick out two distinct people from 40 people. If we evaluate this, it comes out to be 780. Then we calculate the chance that any given pair doesn't share a birthday, which will naturally be 365 divided by 366, as there are 366 possible birthdays, so if one person has one birthday, there are 365 other birthdays that the other person could have, such that they don't share a birthday. Evaluating this cell gives us 0.997. Finally, the probability for each pair is independent, so we can take the multiplication rule of probability to see all of these chances together. This gives us the likelihood that no two pairs will share the same birthday, so we take the complement of this to get the chances that at least two people out of 40 share a birthday as 88%. If we go through and repeat this whole process, except using 60 people, the number comes out to be nearly 100%. Now, if we generalize this problem as a function in the Wolfram language, we can see how fast this probability actually grows. Here, I wrote out a function birthday chance of n, which just generalizes what we did before, and then I used the discrete plot function in the Wolfram language to plot this out as n increases from 2 to 100. As you can see from this graph, from about the 60 to 100 range, you get to a point where you're almost guaranteed to have two people with the same birthday. Moving on, we have a similar problem with permutations. Take the word mathematica. How many possible 11-letter words can be made using only those 11 letters? I should note here that when I say word, I don't mean a correct word, just, a possible string of 11 letters. In this case, order matters, so we start with a permutation. We define a function perm of n comma k equal to our formula from before, and then take permutations of 11 comma 11 in the Wolfram language. Evaluating this cell gives us 39,916,800 different possible 11-letter words, which is vastly an overestimate. And the reason that this is an overestimate is that some words are repeated because of repeated letters. If this were our final answer, we would actually be counting the word mathematica 24 different times, because you can spell it in 24 different ways by rearranging the M's, A's, and T's. To account for this, we can divide by the number of repeated words each repeated letter generates. This gives us our final formula as permutations of 11, 11 divided by permutations of 2, 2 times permutations of 2, 2 times permutations of 3, 3. Evaluating this vastly decreases our final answer, giving us 1,663,200 different possible 11-letter words. Another thing that's interesting about this problem is for any given permutation we take in this problem, k is equal to n, so we can generalize it using only factorials. Here we can confirm this by asking the Wolfram language if it's equal to 11 factorial divided by 2 factorial times 2 factorial times 3 factorial, which comes back true. Now, for solving problems like this, Mathematica's built-in permutation function is actually a little smarter and does this automatically. If we take the length of permutations of m, a, t, h, e, m, a, t, I, c, a in the Wolfram language and evaluate that, it gives us the same number, 1,663,200. I was originally going to title this slide a binomial binomial, as nomial refers to names, so I thought binomial could also mean a word with two different names. However, I found out in a grammar sense of things, binomial usually refers to a phrase with two words connected by a conjunction, or it can refer to a name that uses two parts, like Latin names for species. So I guess this makes binomial a misnomer of nominal nomenclature. So we'll end up using a binomious binomial. Anyway, now our function c of n, k is also referred to as the binomial coefficient of n, k. And this is usually written out with parentheses and n over k. In the Wolfram language, the function for this is binomial of n, k, which, by using a random n and a random k, we can show will always come out equal to our combinations function. Now, an important place this is used is the binomial theorem, which states that for a polynomial x plus a to the power of n, the value of that polynomial will be equal to the sum from k equals 0 to k equals n of the binomial coefficient of n, k times x to the power of k times a to the power of n minus k. Something that's interesting about this is there have been cases of this found in writing from as early as 300 BCE, with a full establishment being written by Al-Kharajhi in the 10th century CE, which is really early for something this big. Another thing to notice is that there's a recurrence relationship here, that binomial of n, k is equal to binomial of n minus 1, k minus 1, plus binomial of n, k minus 1 for n and k greater than 1. Along with that, binomial of n, k is equal to the value in the n plus 1th row and the k plus 1th column of Pascal's triangle. To demonstrate this, we can ask Wolfram Alpha to write out the first 5 rows of Pascal's triangle, and then write a table of the binomial coefficient of 4, k for k equals 0 to k equals 4. Evaluating this gives us 1, 4, 6, 4, 1, which are the same values as the 5th row of Pascal's triangle. Along with that, we can look at Pascal's triangle and see that 1 plus 3 is equal to 4, 1 plus 2 is equal to 3, and 3 plus 3 is equal to 6, demonstrating our recurrence relation. To add to that, the binomial theorem can make it way easier to write out long polynomials. For example, if we take x plus 1 to the power of 4, writing this out can be a pain. However, if we take a table of the binomial coefficient of 4, k times x to the power of k times 1 to the power of 4 minus k, as k goes from 0 to 4, we get the same result. So, if you ever have a situation like x plus a to the power of n, you can just write out Pascal's triangle with n minus 1 places, and then multiply by x and a where necessary. Now, when it comes to a specific permutation of a sequence, we can write it out in a couple of different ways. One of them is two-line notation, where the original elements are listed first, and then their respective images are listed second. Here, we have 1 going to 4, 2 going to 1, 3 to 3, 4 to 5, and 5 to 2. In cases like this, the first line is sometimes left out if the elements have a natural ordering to them, like 1, 2, 3, 4, 5, and so on. Along with that, we can write it out in cyclical notation, which highlights the effect of repeatedly applying the same permutations, showing a cycle of where the elements go. Here, 1 goes to 4, 4 goes to 5, 5 goes to 2, and then 2 goes to 1, with 3 just mapping to 3. Now, if we applied this same permutation to a sequence twice, we can immediately say 1 goes to 5, 4 goes to 2, 5 goes to 1, and 2 goes to 4, with 3 staying at 3, of course. Now, you have all the tools at your disposal to understand the solution to a very famous puzzle. Here we have the 100 prisoners problem. So imagine you have 100 prisoners who are each numbered and given a puzzle to solve as a group. Each one must go one by one into a room filled with 100 cabinets and choose 50 of them to open. The cabinets are each numbered with a prisoner's number, and each one contains a number that's a prisoner's number, but which cabinet contains which number is randomized. So, when given 50 guesses, if each prisoner can pick their number, then all of them will be set free. You probably already realize this, but the probability of success while guessing randomly is essentially nothing. However, there is a strategy that retrieves over a 30% probability of success. The method follows like this. Each prisoner first chooses the cabinet with their own number. If that guess is wrong, then they choose the cabinet with the number they just received. This guarantees that whatever guesses the prisoners are making follow a permutation cycle of the original set of numbers. With 100 numbers, one permutation can only have one cycle with a size greater than 50. Taking this, there are 100 over k ways to create the numbers in the cycle, with k minus 1 factorial different orderings for that cycle. There will also be 100 minus k factorial ways to order the rest of the numbers. Therefore, for any given number k, the number of permutations with a cycle of size k will be 100 over k times k minus 1 factorial times 100 minus k factorial. This is important because if there are no cycles longer than 50, then every prisoner will eventually pick their number, as they'll be on a permutation cycle that will eventually give them their own number. Not accounting for cycles, there are 100 factorial different permutations the cabinets could be in, which allows us to calculate the chance that a permutation has no cycle longer than 50, and thus the group's chance of survival is roughly 31.2%. Now this is pretty cool to me just because it takes a game that seems pretty clearly impossible to win and gives you a non-trivial chance of winning, even though it's still random. Thank you for watching. In this video, we went over permutations and combinations, the pigeonhole principle, and some probability problems that use those concepts. In the next video, we'll go over some different types of partitions and their different uses. I'm Alistair Forsyth, and again, thank you for watching. Bye-bye.